Welcome to another weekly recap. This week we're talking about Taylor series, and my goal today is to really recap all of this material, go through the development of this material, which means I may not have time to do some of the harder examples. We'll do as many examples as we can, but I really want to go through the development of this material because usually the first time you learn it, you struggle with it. It's actually pretty hard stuff. And if you are struggling with it, I'm hoping this video might provide some sort of extra enlightenment on areas that might be fuzzy for you, an alternate perspective, if you will. But before we do that, let's recap what we did last week. So just to recall, right, a power series is a series of this form. A power series centered at x equals a is a series of this form. Some coefficient Cn, right? Every single time I change n equals 0, 1, 2, 3, 4, 5, 6, whatever. My coefficient here is changing. I have a new coefficient every time. Times x minus a to the n. And x is the variable here. You're allowed to plug in numbers for x, right? So it really is a function. It's a function where I plug in a value for x and I get out an output. The problem is I don't always get out an output, right? Depending on what x is and what my coefficients are, I might have a divergent series. And if I have a divergent series, I'm certainly not getting an output, right? So the question is, what values of x am I allowed to plug in? If I think of this as a function, what is its domain, right? What values for x am I allowed to plug in? And the answer is power series are actually really nice because they always converge on an interval. This is the prototypical case. This interval might actually be a single point, right? R might actually be 0. So that interval could just be a single point at a. Or R could be infinite, and the interval is actually the whole real number line. But prototypically, this is the picture you should have in your mind. This converges absolutely on this interval. So here's my center A, and around this interval from a minus r to a plus r, around a, I've got this interval on which it converges absolutely. Right? So this is what this represents. Absolute value of x minus a is less than r. Let's actually modify this. It converges absolutely, to be very precise. Right, outside of this interval, if I go this way off to infinity or off to negative infinity, I know outside of this interval I must diverge. And the endpoints of the interval, a minus r and a plus r, kind of interesting because actually anything can happen there. You can converge absolutely, conditionally, or diverge. That's why I added this extra word here, because it converges absolutely on the inside of this interval. At the endpoints, anything could happen. So we had that, and that led into, I think we finished the section by talking about this particular power series, the sum of x to the n. So all my coefficients here are always 1. It's centered at 0 because I've just got x minus 0 to the n, right? A is 0. And we observe that's actually just a geometric series. It's a geometric series where a is 1 and r is x. So it must converge to 1 over 1 minus x. The catch is geometric series only converge when r is in absolute value less than 1, so this converges to 1 over 1 minus x only on this interval for values of x between minus 1 and positive 1. Well, that means that as functions, right, this is a function, this function looks exactly like this more familiar function, 1 over 1 minus x, not for all values of x, but for values of x between minus 1 and positive 1. Right, so this is a really, really important example. If you haven't committed it to memory, you should. Which brings us back to Taylor series. Okay, so we have this example. Think of this not in the order I've written it or the way I've been discussing this so far, which is this power series equals this function. I want to go in the opposite direction. I want to ask, given a function, if I have a function f of x, when can I represent it as a power series? And that's exactly what we're doing here, right? I'm taking this function f of x, and I'm rewriting it as a power series. It doesn't work for all values of x, only for these ones between minus 1 and positive 1. But what if I have another function? and I ask this question. I give you a function, I say, let's express this as a power series. The first question is, can you even do that, right? So here's our question. Given a function f of x, when can we express f of x as a power series? And maybe not for all values of x, but at least on some interval, right? So on some interval. Let's say centered at, maybe not even centered, too strong of a word, just containing x equals a. Well, let's suppose we can. Suppose we can. Right, so that is suppose I can write f of x as a power series. Some coefficient c sub n times x minus a to the n as n ranges from 0 to infinity. Okay, so you've given me this function, and I've just said, well, suppose we can write this as a power series centered at x equals a. Right, so suppose I can do this. What can we gather from this? Well, I've run out of space on my board, so I'll be with you in just a moment. Okay, so this is where we were, right? We said suppose we can write our function as a power series centered at x equals a. I don't know the interval of convergence or anything here, but I'm assuming it converges on some interval containing a. Alright, so yeah, suppose we can do this. Well, what I want to do is look at the derivatives. Right? If they're equal, then they should have the same first derivative. So let's differentiate this, and to do this, I tend to like to work term by term. I'm going to count out the first few terms here. So if n equals 0, we're looking at c sub naught times something to the power 0, which is 1. If n equals 1, we've got plus c sub 1 times x minus a to the 1, which I'm not even going to write, plus c sub 2 times x minus a squared, plus c sub 3 times x minus a cubed, plus c sub 4 times x minus a to the 4th, and so on. Okay, so there's our power series expansion. And I'm going to differentiate this, right? The left-hand side equals the right-hand side, so they should have the same derivatives. So f prime of x should equal the derivative of the right-hand side. Derivative of c naught is a constant, so it just differentiates to 0. Derivative of c1 times x minus a, well, derivative of x minus a is just 1 minus 0, so just 1. So this is c1 times 1. Plus, what about this? Well, if I differentiate x minus a squared, I have to use the chain rule here. So the 2 comes out front, 2 times x minus a to the power of 1, right? Lower the power by 1, and then multiply by the derivative of the inside. But the derivative of x minus a is just 1, so all in all, this becomes 2 times c2 times x minus a. What about the next one? Well, again, use the chain rule. So 3 comes out front, 3c3 times x minus a squared, right? Lower the power by 1, and the derivative of the inside is always, derivative of the inside x minus a is just 1, plus 4c4 times x minus a cubed, and so on. Okay, so there's my first derivative. If I can write this as a power series, then I must have the derivative is equal to this expression. Let's keep going. Let's do the second derivative. Derivative of c1, 0. Derivative of 2c2 times x minus a is just 2c2. Now, derivative of this expression, 2 times 3, which I'm going to write as 2 times 3, not 6. So we can start to develop patterns here. Times c3 times x minus a to the power of 1, plus 3 times 4 times c4 times x minus a squared, and so on. I'm going to keep going. We'll just do this one more time. The third derivative This is a constant differentiates to 0. I've got 2 times 3 times c3 plus, what about this? Derivative of this guy? 2 times 3 times 4 times c4 times x minus a plus some other stuff. What do you notice here? Notice I haven't written out as many terms as I'd like. If I had a bit more space, we might count out to the 5th power to start. But I've got these products of 4 times 3 times 2 times 1. That's a factorial, right? And this is why factorials are so important in mathematics, because they pop up very naturally in many areas. In this case, repeated differentiation. Well, let's see. Do you think we could come up with, let's not do this yet. Okay, so there's my derivatives, right? There's my derivatives. There's one point in particular that's really interesting. They're true for some values of x, but they're at least true for x equals a. Let's plug in x equals a. Alright, so if x equals a, then what do we have? We've got f of a, plug in f of a into this, so plug in a into x. F of a equals c naught plus what? Plus c1 times a minus a, which is 0, c2 times a minus a squared, which is 0, c3 times a minus a cubed, which is 0. So all those other terms disappear. They go to 0, and I'm just left with c naught. What about f prime of a? F prime of a, plug in a into this guy, f prime of a would equal c1 plus 0 plus 0 plus 0, so this is just c1. F double prime of a, plug in a into this guy, 2c2 plus 0 plus 0 plus 0, so 2c2. F triple prime of a, what do I have here? I've got 2 times 3 times c3 plus 0 plus 0 plus 0. 2 plus 3, or sorry, 2 times 3 times c3. Can you see what would happen? I haven't written it out, but what if I did the 4th derivative? The 4th derivative, sometimes people put 4 in brackets there. I'll just do 4 primes, and this is at a. What would the 4th derivative be? This would go to 0. I would have 2 times 3 times 4 c4 plus some stuff. So when I plug in a, I'm going to have 2 times 3 times 4 times c4. Do you think we can pull a pattern out of this? Can you guess what the nth derivative at a would be? The nth derivative at a. Well, the first derivative was just c1. Second derivative was 2 times c2. Third derivative was something times c3. Fourth derivative was something times c4. So pretty clearly we're going to have something times cn. Right? This guy, you can think of this as the 0th derivative. So we've got c sub 0. What about the coefficient in front? Well, this looks like 4 factorial, right? This is 3 factorial. I just haven't written the 1 in the product here. This would be, you can write that as 2 factorial, 1 factorial, and 0 factorial is defined to be 1. So everything works out nicely with patterns. So this is actually n factorial times cn. Just trying to come up with a pattern for what's happening here. The nth derivative at a looks like n factorial times cn. And that means that c sub n looks like, or is actually equal to, the nth derivative of f at a over n factorial. So that means if I can write f of x as a power series centered at x equals a, it must look like the following. It must look like f of x equals n equals 0 to infinity. We had c sub n times x minus a to the n, but by going through this exercise here, we've discovered that my coefficients must look like this. They must look like the nth derivative of f at a over n factorial times x minus a to the n. And this expression is called the Taylor series. The Taylor series for f of x at, or centered at, x equals a. I'm not claiming that they're equal. Sometimes they're not equal. Sometimes you'll build this power series and it doesn't really have anything to do with f at all, right? But if I can do this, if I can write this as a power series, it must take this form. My coefficients have to look like that. So this particular power series, you start off with a function f, and based on f, you can build all these coefficients. You can build this power series based on f. This power series is called the Taylor series generated by f of x at x equals a, or for f of x at x equals a. The particular case, when you take a to be 0, you would get the nth derivative of f at 0 over n factorial just times x to the 0, or x to the n. This is sometimes called a Maclaurin series. Is it an I or an E? I can never remember how to spell it correctly. It is an I. Alright, this is called a Maclaurin series. I don't like calling things Maclaurin series. It's not part of my vocabulary. It's really just a Taylor series at x equals 0. Alright, so this is a Taylor series at x equals 0. For whatever reason, in Calculus 2 classes, people usually teach this term Maclaurin series, but it's just a special case of a Taylor series. It's when you take the Taylor series at x equals 0. Right? So without introducing more confusing terminology, this is what I'm going to call it from now on. It'll be a Taylor series at 0. So this is our first example. Find the Taylor series for the function f of x equals sine x at x equals 0. Well, how do we do this? Well, we have a formula, right? We have a formula for the Taylor series. It's going to be the sum of the nth derivative at 0 over n factorial times x minus a, but a is 0, x to the n. Right? So commit these formulas to memory. Commit the general form of a Taylor series at x equals a to memory, and then this is all we have to do, which means really the question boils down to figuring out what these guys are. What is the nth derivative of sine of x at 0? We'll see if we can figure this out. F of x is sine x, so that means f of 0 is sine of 0, which is 0. What about my first derivative? First derivative, cosine of x. So that means my first derivative at 0 is 1. What about the second derivative? Second derivative is minus sine x, which means my second derivative at 0 is 0. My third derivative, minus cosine of x. So my third derivative at 0 is minus 1. Sorry about that. I plug in 0 into minus cosine of x to get minus 1. And then what happens? At the fourth derivative, derivative minus cosine of x, we're back to sine x. Right, so once again, this is 0, and the pattern repeats. Right, so my derivatives look like 0, 1, 0, minus 1, 0, 1, 0, minus 1, and so on. So if I was to start plugging these in, what are we going to have? Well, let's go by term. So n equals 0, I've got the function evaluated at 0, which is just 0. Over 0 factorial times x is 0, but 0 times anything is 0, so I'm just going to write 0. Plus n equals 1, first derivative at 0, which is 1, over 1 factorial times x to the 1. Right, plug in n equals 2. Plus n equals 2, we're going to have second derivative at 0 is 0, so 0 times anything is 0, so I just write plus 0. And now we're at the third derivative, so now we're going to be minus 1. Minus 1 over 3 factorial times x cubed. Alright, what's next? Fourth derivative is 0, so we're going to be looking at plus 0. Then we've got the fifth derivative. Well, this is where we start looping, right? Third derivative goes back to the beginning. So fifth derivative should be 1. So we're going to have plus 1 over 5 factorial times x to the fifth. And I'll start dotting it off because I'm totally out of space. But 1 over 5 factorial times x to the fifth. And if I don't write the zeros, because I don't really need to write them to figure out what this looks like, let's just clean this up a little bit. This will be 1 over 1 factorial times x. Let's skip out all the zeros. Minus 1 over 3 factorial times x cubed plus 1 over 5 factorial times x to the fifth. Now if I say dot dot dot, you should be able to figure out what the next term is. Think about what the next term is for a moment. Look at the pattern here. What should the next term be? Well, I'm only doing odd powers of x. My factorial on the bottom matches the power, and I flip the sign every single time, right? So the next term should be minus 1 over 7 factorial x to the 7 plus dot dot dot. Again, totally out of space. So that's the Taylor series for sine of x. The dot 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 indicates that you can figure out what the next terms are. The pattern's clear. This is sort of a learned skill. It's a little bit hard to go back to summation notation, but in summation notation, the nicest way to write this is as n equals 0 to infinity of f. Oops, sorry. Why am I going back to f? What are my coefficients here? Well, I've got something over odd factorials. So on the bottom, I've got 2n plus 1 factorial. Right? If n is 0, I'll be looking at 1. If n is 1, I'll be looking at 3. If n is 2, I'll be looking at 5. So this does count out all the odd integers. We've got x to those powers, so x to the 2n plus 1. And then I just want something that alternates signs. So minus 1 to a power. And if I do minus 1 to the n, that will start on the positive power, or on the positive 1. And as n equals 1, 2, 3, it will alternate plus, minus, plus, minus. So this is actually the Taylor series expansion for sine of x. Around x equals 0. Turns out you want to commit this one to memory forever, right? So this is another one that you want to commit to memory. Does it actually equal sine x? It turns out it does. It equals sine x for all values of x, but we haven't proven that yet. We're just starting off with here's a function. Let's build this associated power series that's associated to it, right? And we'll show that it actually equals sine of x. But not yet. All right, we'll do another one. Find Find the Taylor series for f of x equals 1 over x squared at x equals 1. Okay, so remember, we're looking for this expression, the sum of the nth derivative of f at, not 0 this time, we're doing it around x equals 1, so at 1 over n factorial times not x to the n this time, but x minus a, right? X minus 1 to the n. N equals 0 to infinity. So once I've identified the form I'm looking for, again, there's only one piece of work we have to do really, which is identify that expression there. What is the nth derivative of f at 1? Well, let's see if we can figure this out. So we've got f of x, 1 over x squared. If I'm going to differentiate that, it's a lot easier to think of this as x to the minus 2. Right? So f at 1 is just 1. So there's the 0th derivative. First derivative, differentiate this, we've got minus 2 times x to the minus 3. So evaluated at 1, what is that? Plug in 1, this is just 1 over x cubed, so plug in 1, that's always going to be 1. So minus 2. Second derivative, what do I have now? I've got minus 2 times minus 3 times x to the minus 4. Haven't left myself quite enough space here. But this equals, if I plug in 1, I've got minus 2 times minus 3 times 1. So I'll just write this as 2 times 3. Again, I don't want to multiply them together to get 6 because that sort of kills the pattern identification. It's hard to identify patterns if I just multiply these together. Third derivative. We're going to have minus 2 times minus 3 times minus 4 times x to the minus 5. So now if I plug in 1 into this, I've got 3 minuses, makes it minus 2 times 3 times 4. So minus 2 times 3 times 4. So perhaps you can identify the pattern now. Perhaps you can identify the pattern. What do you think the nth derivative at 1 is? Well, I'm clearly alternating signs, right? I start off positive, minus, plus, minus, plus, minus. So I want to have a minus 1 to the n type thing. And if I do minus 1 to the n, that'll make us start positive, right? So we'll do minus 1 to the n. If n is 0, we're positive. If n is 1, we're negative. If n is 2, we're positive again. What about this thing? How does this number here relate to the derivative? Well, for the first derivative, we've got 2. For the second derivative, we've got 2 times 3. For the third derivative, we've got 2 times 3 times 4. So it's a factorial again, but it's always 1 bigger than the number of derivatives we took, right? So this looks like n plus 1 factorial. Alright, so if n is 3, we have 4 factorial. If n is 2, we have 3 factorial, and so on. So just looking at the pattern here, thinking about what happens if I differentiate more and more times, that should be the nth derivative. So this means that our Taylor series is going to be minus 1 to the n times n plus 1 factorial over n factorial times x minus 1 to the n. And I can actually clean this up a lot, right? I can clean this up a lot because I've got n plus 1 factorial over n factorial. Oops, n equals 0 to infinity. That is the worst sigma I've ever drawn. n plus 1 factorial over n factorial. Remember what this is n plus 1 times n factorial. So n plus, let's see, that's n plus 1 times n factorial, and the n factorials are going to cancel, right? So we're really looking at minus 1 to the n times n plus 1 times x minus 1 to the n. And there's the answer. So all the work goes into two places. One, knowing the form of a Taylor series and writing down the right form. Make sure you've got x minus a. A is 1 in this case. And we also evaluate our derivatives at a, so 1 in this case. And the other part is, once you have the form correct, is you just have to figure out what is my nth derivative at 1, which usually amounts to write down a bunch of derivatives, and then you can identify a pattern, hopefully. So there's our Taylor series. And I want to do a little bit more with this. What if I wrote out the first few terms? What if I wrote out the first few terms? So n equals 0, what do we have? We've got positive 1 times 1 times 1. So that's just 1. I'm not going to worry about the minus 1 to the n anymore. I'm just going to remember that that causes me to alternate signs. So now I'm looking at minus n equals 1. I've got 2 times x minus 1. And then I go plus, n is 2. We have 3 times x minus 1 squared. And it's not too hard to identify the pattern here. This number is just increasing 1 every time. My power is increasing 1 every time, and I'm alternating the sign. So this will be minus 4 x minus 1 cubed plus 5 x minus 1 to the 4th minus 6 times x minus 1 to the 5th, and so on. All right, there's my power series expansion. I have no idea if this converges. I haven't thought about it. I don't know if it equals the original function or where it does. I haven't done that either. But this is the so-called Taylor series for this function. Now what I want to do is introduce another term, another expression, which is the nth order Taylor polynomial. And the nth order Taylor polynomial is just the Taylor series, but truncated after the nth power of x. Right? So, for example, if I said find p sub 3, the third order, Taylor polynomial, I would just count out to the third power of x. 1 minus 2 times x minus 1 plus 3 times x minus 1 squared minus 4 times x minus 1 squared. No, that is 4x minus 1 cubed. I've hit the third power of x, so I'm going to stop there. Right? So p sub 3 is just count out to the third power. Right? So the power here is important. If I said find the fourth order Taylor polynomial, p sub 4, you would count out to the fourth power, and then truncate the rest, just cut it off. Right? So it's a finite polynomial. And that's really all there is to Taylor polynomials. Alright, so I've sped ahead here, and I've got a problem written up on the board, and I've done most of the heavy lifting already. So here's the question. Find the second order Taylor polynomial, p sub 2 of x, for f of x equals sine squared x, and we're going to do this at x equals 0. Right, so what I've written down here is here's the Taylor series, right? The infinite Taylor series, nth derivative at 0 over n factorial times x to the n. If I expanded this out, this looks like f at 0 over 0 factorial, which is just 1, plus f prime of 0 over 1 factorial times x, plus f double prime f double prime at 0 over 2 factorial times x squared plus f triple prime at 0 over 3 factorial times x cubed, and so on, right? If I only want the second order Taylor polynomial, then I'm only looking for this expression, right? I'm looking to truncate the expression after the squared term, after the second power, because this coefficient there, or the subscript there, matches the power here. Okay, so p sub 2 means I want to count out to the second power of x. So I know the form of p sub 2. The only unknowns here, the only pieces I need to figure out is what is f of 0, what is f prime of 0, what is f double prime of 0. So I've gone ahead and computed these. F of 0, or f of x is sine squared x, so plug in 0 to that, you can just get 0. Take the first derivative. This is a derivative that Calculus 2 students often mess up, but remember it's chain rule. This is sine of x squared, so the derivative would be 2 sine x times the derivative of sine, which is cosine. Plug in 0 into that, you still get 0. And f double prime of x, take the second derivative, so applying the product rule to this is minus 2 sine squared x plus 2 sine squared, or 2 cosine squared x. And plug in 0 into this. This first term is 0, I've got 2 times 1, so my second derivative at 0 is 2. Which means p sub 2 of x, my second order Taylor polynomial, is just 2 over 2 factorial times x squared. Well, 2 and 2 factorial cancel, and the answer is just x squared. By the way, what if I said, what's the first order Taylor polynomial? What's p sub 1? Well, that would be truncate this after the first power, right? Well, if I truncate this after the first power, I just have 0 plus 0 times x. So my first order Taylor polynomial is 0. You'll notice it's not a degree 1 polynomial, because all my coefficients are 0, and sometimes that happens. That's why I'm not saying the nth degree or the second degree Taylor polynomial, because this doesn't necessarily refer to the degree. I'm saying the order. Count out to the second power. In this case, we count out to the first power. It just so happens my coefficient of x to the first power is 0. So my Taylor polynomial is 0 plus 0. And that can happen. That's totally fine. But I think that concludes this section on Taylor series. So there's exactly 2 skills you should have out of this section. Right? 1, if I give you a function, be able to build the Taylor series. Expand it around, or build the Taylor series generated by f at x equals a. Right? So there's your first skill, being able to build a Taylor series. And the second skill is very closely related, being able to find Taylor polynomials, being able to truncate that. Right? So instead of counting out infinitely many terms, just count out n of them. So 2 skills: find Taylor series, find Taylor polynomials. So we started off with this question of, if I give you a function, when can you represent it as a power series? Right? When can you write it as a power series? And this led us down this road of, well, if I can write it as a power series, it must look like this so-called Taylor series for the function. Right, but we haven't established equality yet. We haven't answered this question of, is it actually equal to its Taylor series? And the answer is maybe. Right, that's honestly the best answer. It's maybe it equals it. But in certain cases we can demonstrate that it actually does equal it. So suppose, again, here's just my function f of x. What I always can do, right, I'm not going to claim it equals its Taylor series, but what I can claim it always equals is take any nth order Taylor polynomial, right? So think of that as being an approximation of our original function. But I'm only counting out n terms, so I'm not doing infinitely many terms here. So it's only an approximation, plus some extra remainder, right? This is an approximation. It's not exactly equal to f, so there should be some difference between them. Their difference is, excuse me, is the remainder over here. And it turns out, here's the fact, if the remainder term tends to 0, as n tends to infinity, for all x on an interval, I, then f of x is actually equal to its Taylor series expansion. N equals 0 to infinity times x minus a to the n for some a in this interval I, where a in I. Okay, so the point is that so this, I can think of the nth order Taylor polynomial as being an approximation. The point is, if I let n get bigger and bigger and bigger, so I count out more and more and more terms in my Taylor series, if that's becoming a better and better and better approximation, so this thing is shrinking off to 0 and disappearing, if this gets to be a better and better approximation as I count out infinitely far, then my function is indeed, and this shouldn't come as any surprise because this is just a truncated version of this, if as I count out infinitely far, my remainder shrinks to 0, then my function actually does equal this, this Taylor series expansion for some choice of a in the interval on which this actually happens, on which this remainder shrinks to 0. So I don't want to dwell too much on that convergence stuff, on the remainder, r sub n, and whatnot. I do believe you might have a homework question or two based on placing bounds on the remainder, and you can look up how to do that. So in the interest of time, I'm going to jump ahead here to some very important results, which are, using that remainder stuff, we can show that certain functions are actually equal to their Taylor series for some intervals, right? For some values of x. And the first one, we've already done this one, so this one is a given, but 1 over 1 minus x as a Taylor series is equal to x to the n for x just between minus 1 and positive 1. But if you built the Taylor series for e to the x, you would get the sum of x to the n over n factorial, and you can show that that actually converges. These are equal to each other for all values of x. Doesn't matter which value for x you plug in into this summation, you will get e to the x. Right, so exact same functions. Sine of x we already built. We built the Taylor series for sine of x, and it turns out that that Taylor series is equal to the function sine of x for all values of x. So it converges everywhere, which is really nice. And you can build the Taylor series for cosine of x if you want, but I've listed it as 3.5 because once you know sine x, you automatically know cosine of x. All you have to do is differentiate it, right? Derivative of sine is cosine, and if this power series equals sine of x, then its derivative, differentiated, I promise you'll get this, should equal cosine of x. So if you know sine, you know cosine. And I'm saying these are important because you need to memorize these. These have to be part of your list of power series that you've memorized because you're going to use them all the time. And the reason we use them all the time is because if someone says, find a Taylor series or find a power series representation of a given function, it's really hard to do it the way we've been doing it, right? It's really hard to find all infinitely many derivatives, evaluate them at a point, and then even if you can express it as a Taylor series, you don't know that it converges, you don't know that it's actually equal to it, you'd have to go through and prove some convergence results, right? That's a lot of work, that's hard stuff. But what I can do instead, most often, is take these 4 known power series and manipulate them. And this is an example, right? If someone said find a power series for cosine of x, all they'd have to do is take sine x and differentiate it. But there's other things we can do. We can integrate, we can make substitutions as you were doing last week. We made substitutions on this guy, we plugged in like x squared, stuff like that. You can multiply power series together. So we can do quite a lot of manipulation here, and this is the easy way to go. It's much easier than having to show convergence properties for given Taylor series that you've built. Okay, so for example, let's say someone says find a power series representation for of x equals e to the x sine x at x equals 0. So I know if 1 exists, it must be its Taylor series, right? It must be its Taylor series at x equals 0. And what you could do is you could build the Taylor series as we've just been doing. You could go through and build the Taylor series. You could find all the derivatives at 0. The problem is that gets old really quick, right? Differentiating this many times over is pretty painful. And then even if you built the Taylor series, you don't know if it actually equals the original function, right? You would have to go through and do these convergence properties. So instead of doing that, what I'm going to do is just recognize that I'm allowed to multiply power series together, and I know Taylor series, power series representations of both of these functions, right? So this would be the sum of e to the x is x to the n over n factorial. And sine x is the sum of minus 1 to the n times sine is, I always have to remember sine is the odd powers, cosine is the even powers. X to the 2n plus 1 over 2n plus 1 factorial, n equals 0 to infinity. These converge for all values of x, so when I multiply them together, it's still going to converge for all values of x, and I automatically have this convergence stuff done. Now I just need to multiply them. This is technically, if you look through your textbook, this is this convolution formula will tell you the coefficients of the powers of x here. But I've always found the easiest way is just to do the multiplication by hand. I can never remember the formula. So let me count out the first few terms here. This would look like n equals 0, we've got 1, plus n equals 1, we've got x, n equals 2, we've got 1 over 2 factorial x squared. How far do I want to go? We'll go to the cube term, plus 1 over 3 factorial x cubed, and plus dot dot dot. I'll start dotting it here. Times, we'll write out the first few terms here. This will look like 1 minus 1 over 3 factorial x cubed, plus 1 over 5 factorial x to the 5th. And that should suffice, minus dot dot dot. Okay, so I want to multiply these together. I want to write this as an actual power series, right? It's not a power series right now. This is not the form of a power series. It's got to be a coefficient times x to the n. So I want to multiply these together. And the easiest way to do this is just to think about how, as I multiply this, right, obviously this means this whole expression times 1, plus this whole expression times the second term over here, plus this whole expression times the third term. Well, I can't multiply an infinite amount of stuff times 1 and then add that to another infinite amount of stuff and whatnot. But what I can do is I can just ask, how do we get increasing powers of x? Right? Are there any ways to get constants? And the answer is yes. I could do 1 times 1. So that's the only way I have a constant in this expression is 1. Can I get powers of x to the 1? Well, if I do 1 times any of this stuff, I'm not going to get x to the 1. But I could do x times 1 to get an x term. And I think that's the only way I can get x to the 1. If I do x squared times any of this stuff, I get x squared terms. So yeah, we can't do that. What about x squared terms? Can I get x squared? I could do 1 times this stuff, I don't get any x squared terms. I could do x times this stuff, I don't get any x squared terms. I could do this expression times 1 to get an x squared term. So plus, x squared times 1/2. And that's the only way to get an x squared term. Now it becomes a little bit more interesting. How do I get x cubed terms? Well, I have 1 times minus 1 over 3 factorial 1 over 6 times x cubed. So I've got minus 1/6 x cubed from that multiplication. But there is another way to get an x cubed term. I could do x times 1. So plus 1. And that would be all my x cubed terms if I did this infinite multiplication. And then you keep playing this game. Can I get x to the 4th terms? X to the 4th. How do I do this? Oh, I haven't written it here. How about I expand this just a little bit? 1 over 4 factorial x to the fourth plus dot dot dot. Okay, x to the fourth. I could do x times minus 1 over 6x cubed, so minus 1 over 6 x to the fourth from that multiplication. Or I could do, I think, x squared times all this stuff doesn't give me x to the fourth terms, x cubed times all this stuff doesn't give me x to the fourth terms, but this guy, 1 over 4 factorial times x to the fourth times 1 gives me an x to the fourth term. So this is plus 1 over 4 factorial is 1 over 24. And so on, plus x to the fifth times some stuff and whatnot. So this, even though I'm dotting it out, I haven't really sort of figured out what the pattern for the coefficients here is, and I suspect it's a very ugly pattern. But this is at least the first 4 terms in the power series representation for this function. And I know it must equal this for all x. Why? Because these original 2 power series converge for all x, so their product converges where they both converge, which is all values of x. So without having to do a whole bunch of differentiation, without having to prove convergence results, I just used stuff that I knew about the original, these 2 functions, and I use that to build a new power series. It's a much easier way to go about this. We'll do one more example. Okay, so I want to find a power series representation at x equals 0 for arctangent of 2x. Well, this doesn't look like any of our 4 memorized ones, right? We've memorized power series expressions for 1 over 1 minus x, e to the x, sine x, cosine of x. This doesn't look like any of those, but it is the integral of something that looks like one of those, right? So let's differentiate this. The derivative of arctangent of 2x, what does this differentiate to? Well, arctangent differentiates to 1 over 1 plus the argument squared, so 4x squared, times the derivative of the inside, times 2. So actually 2 over 1 plus 4x squared. That looks a lot like 1 over 1 minus x. I just need to manipulate 1 over 1 minus x to look like this. Alright, so that's what we're going to do. So let's see, we've got x to the n equals 0 to infinity. That's 1 over 1 minus x, right? Not for all values of x, just for absolute value of x is less than 1. What I'm going to do is I'm going to multiply by 2, right? So next step, I want to manipulate this to look like this. So I'm going to multiply by 2, so 2 times x to the n is 2 over 1 minus x. And that hasn't changed where it converges at all, right? Just multiplying by 2 does nothing. But now I'm going to do something pretty significant. I don't want 1 minus x, I want 1 plus 4x squared. So what I can do is I can substitute. I can substitute minus 4x squared everywhere I see an x. Okay, so everywhere I see an x, I'm going to plug in minus 4x squared instead. So we're going to have minus 4x squared to the n. That's going to equal 2 over 1 minus 4x squared, which is plus 4x squared. And where does this converge? Now this converges for absolute value of minus 4x squared is less than 1. Alright, so you're allowed to make these substitutions as long as you're substituting in a continuous function of x. And we need to clean this up a bit. What do we have? Minus 4 to the n. Oops, this is n equals 0 to infinity, so we'll clean this up quite a bit before we do anything else. This is 2 times minus 4 to the n, I'm going to write that as minus 1 to the n, times 4 to the n. I'm actually going to write 4 to the n as 2 to the 2n. right? Instead of writing 4 to the n, I wrote as 2 to the 2n, right? 2 squared to the n, so that I can group these together. And then we've got x to the 2n. That equals 2 over 1 plus 4x squared. Where does it converge? Well, now this converges for minus doesn't really matter, right? Inside absolute values, minus doesn't matter. I can just erase that. And if I want to solve for x, well, I would divide by 4, right? So divide both sides by 4, and we're going to have absolute value of x squared is less than 1 over 4. Or, if I want just x, I should square root this, right? So, or absolute value of x is less than 1 over 2, taking the square root of both sides. So I have changed the convergence properties of this. It no longer converges from minus 1 to positive 1, it converges from minus 1/2 to positive 1/2. Alright, so, bringing this, let's see, I want an arrow for my work. Okay, so bringing this back over here, I'm going to do one more bit of manipulation. I've left off my subscripts, indices, whatever. We've got n equals 0 to infinity. I'm going to write the minus 1 to the n first. It's sort of customary to do that if you have it, so minus 1 to the n first. 2 times 2 to the n, that's 2 to the 2n plus 1, right? Adding the exponents, this is 2 to the 1. So you add the exponents together there, times x to the 2n, that equals 2 over 1 plus 4x squared. And I know where it does it. They're equal to each other for x from minus 1/2 to positive 1/2. So this is a power series, right? It's a power series. This is some coefficients times x to the n. It's centered at 0. X to the 2n means I really only have even powers of x, right? All the odd powers of x are multiplied by 0. So what do I need to do now? Well, remember, this was the derivative of this guy. So if I want a power series representation of arctangent, all I have to do is integrate this. So we'll integrate both sides. The integral of the left, well, minus 1 to the n, 2 to the 2n plus 1. I'm integrating with respect to x, right? So x to the 2n integrates to increase the power by 1, x to the 2n plus 1, divided by the new power, 2n plus 1. N goes from 0 to infinity. The integral of the left should equal the integral of the right. And the integral of the right-hand side is arctangent of 2x. With one catch, when I integrate, we always introduce a plus c, right? So this is actually arctangent of 2x plus c. Now if you forgot this, sometimes it disappears. In this case it will, but the plus c should be there, and you do technically have to check this. And by the way, when does this converge? For, well, integrating, we're guaranteed you still converge on at least the same interval you started with. So when I integrate, I still converge at least on the absolute value of x is less than 1/2. So thinking about this plus c really quickly, what if I plug in x equals 0? If I plug in x equals 0, and I start counting out the first few terms of this, what do I have? Right, well, if I plug in x equals 0, what do I get? Well, I never have a constant term on the left, right? If n equals 0, I've got x. If n equals 1, I've got x cubed. If n equals 2, I've got x to the 5th. I never have a constant term on the left. So if x equals 0, I'm just going to have 0 on the left equals arctangent of 0 plus c. So that means c is actually 0. So in this case, my answer, my power series expression, or representation of this function arctangent of 2x is just this. Alright. So yeah, this video is quite long already. I think we'll stop here. The goal next week is hopefully I can get something out early, say by Wednesday or Thursday, because there's really only one class to cover, which is Monday's class. We'll do a lot more of the Taylor polynomial stuff. We'll do applications of that. So if you're not super comfortable with it yet, hopefully you will be after that class, because we'll do a lot more examples. Thanks.